Hello everyone, I'm Carl Zielinski. Today we will be making a little Breakout game using Odin and Raylib. Breakout is this game from the 70s where you have a little paddle that you control and a ball can hit it, and there are some blocks that you hit and you get points by hitting those. There are also famous sort of improved versions of Breakout, the most famous being perhaps Arkanoid. But we will just be doing like a simplified Breakout-ish clone here. So I will be using the Odin programming language. I have a separate video on how to set up the Odin programming language. That video is linked in the description of this video. And we will be using Raylib. Raylib is a library for drawing graphics, processing input, playing sounds, and Odin comes with built-in bindings for Raylib. So the text editor I will be using is Sublime Text, and I have a separate video on how to set up Sublime Text for development with the Odin programming language. But essentially I have here a file called breakout.odin, which is completely empty. This breakout.odin file is inside a folder called Breakout, and there I also have my Sublime project. And this Sublime project is set up just like in the video where I show how to set up the Sublime stuff. And on the right here I have an outline of what we will be doing today. So let's jump into the first point here. Create a window plus main loop. All Odin files must start with a package definition. So we just write package space breakout. And this package line must be the same for all files in the same directory. And you may also notice that we have chosen the name breakout here and that the folder is called breakout. It doesn't necessarily have to be like that. The name on this package line here is for ABI linking, meaning that if we use our code as a library, it is used by the linker to uniquely identify our code. But for a simple game like this, it doesn't really matter what you put there as long as it is the same for all files in the same folder. I have said that we will use Raylib, so Odin comes with built-in bindings for Raylib. So we can just import that stuff. So we write import rl vendor :raylib. This will make it so that the stuff inside the Raylib package is available under the name rl, which we will see soon when we use it. So our program has to start somewhere. By default, Odin looks for a procedure called main. So we create this main procedure by typing main : proc, some parentheses and some curly braces. So this creates a new procedure called main. So using Raylib, we can open a window by typing rl.init window. And this init window wants a width, a height and a title. So I will choose the width 1280 and the height 1280. So it's sort of a square window. And then I will choose the title breakout like that. And after that, we need a loop that runs for as long as the window is open. And we do that by typing for !rl.window should close, some parentheses and some curly braces. So this loop here, this for thing, this creates a loop and it will continuously run the stuff between this curly brace and this curly brace as long as this condition holds true. And this loop is what is known as the sort of main loop of the game. All the logic for each frame of the game is happening in between these curly braces here. So inside this loop here, we will type rl.begin drawing. This tells Raylib that we are starting drawing a new frame, and then we type below it end drawing. And after that, if the window should close, then just before the main procedure terminates, we should also close the window. So we type rl.close window here. If we compile and run this program like this, and I have my Sublime stuff here set up, so I can just press F7 to do this, then we see that we get this black window that says breakout on the top and it's sort of square. So we can close that. We want to put in sort of a nicer background color here, so we will type rl.clear background like this, and this clear background expects a color. A color in Raylib is 4 numbers that go between 0 and 255 each. So I will type like this, 2 curly braces, and then I write 150, 190, 220, 255. This is the red part, this is the green part, this is the blue part, and this is the alpha. So if we now run our program, we have this sort of light blue background color instead. Finally, before we move on, I just want to add two things at the top here. So one thing is that I want to enable vertical sync. This makes it so that our program waits for the screen to be finished with updating the picture before it tries to give it the next one. This can prevent what's known as tearing, where it looks like the sort of picture is sort of cut in half. So you set that up by writing rl.setConfig flags, some parentheses, and you create these flags by putting some curly braces like this, and then you can write .vsync hint. In most cases, you need to set up your config flags before you init the window, otherwise some of them might not be respected by the window that is created. On top of that, I also want to set a FPS limit, or like a frame rate limiter, and I will put just after init window here rl.set target FPS 500, so that our game cannot run at more than 500 frames per second. Now, the slightly technical person here might realize that vsync usually implies a maximum frame rate, since if the monitor is a 60 Hz monitor, that means that it can only update 60 times per second. So this thing here actually on my 60 Hz monitor already limits the game to 60 frames per second. But on some computers, people have forced vsync off, and in that case, the game would run at like thousands of frames per second, and your GPU will make noise and your battery will drain. So I just tend to put in this little extra target FPS thing here just to have a reasonable upper limit to the frame rate. So in Breakout, you control this little what's known as a paddle, which is the thing at the bottom that you control from side to side and that the ball can bounce on. So the first thing we need to know is sort of where on the screen is the paddle. So we will write paddle pos x colon F32 here, just create a global variable just before the main procedure here. So this variable is of type F32, which is a 32-bit decimal number. And in Odin, variables are default initialized to 0. So this actually means that there will be a 32-bit floating point number that is of value 0. So we also need to know how big, both wide and high, the sort of player paddle should be. And I will make two constants called paddle width and paddle height for that. Paddle width in all caps like this, colon 50, and paddle height, colon 6. So this is just a naming convention here that constants, which are created with a double colon, have all caps with an underscore between words like this. And constants, as the name implies, cannot ever be changed. This is a variable, it can be updated. It starts at the value 0 in this case, since I'm not giving it a specific value, but it can be updated. Meanwhile, the constants cannot. And finally, I want to know where on the screen, height-wise, should the paddle be. And I call it paddle pos y colon 260. And as you can see, this is also a constant because I only expect to move the paddle sideways, but I never expect it to move up and down. So now we can try drawing our paddle. Initially, I will just draw it as a box. Later, we will replace this box with some graphics. But for creating a box, we need to define a rectangle, and Raylib has sort of a concept of rectangles. So what we can do here is just below the clear background row, but before end drawing, we will type paddle underscore rect colon equals rl.rectangle, some curly braces, and in between here, we will type out the values of this rectangle. And a rectangle has a x position, a y position, a width, and a height. And they come in that order. So we can write paddle pos x, because that's the x position, and the y position is paddle pos y, and then the width is paddle width, and the height is paddle height. You may notice here that up here we have a colon to create this variable, and down here we have a colon equals. This is because we're also giving this variable a value. It is not just initialized to 0. And furthermore, if we compare these two lines, then in this case, the type name rl.rectangle seems to not be directly after the colon here. So what we could do here actually is we could take the type and put it just after the colon like this instead. Now these two lines look more similar. There is a colon and then comes the type name. and then there's the equal here. But when you both create a variable and set its value on in one go like this, then you can just put the type on the right hand side like this, and this is called type inference, and it just means that we figure out the type of this variable based on whatever is on the right hand side of this equal sign here. Now let's draw the paddle. So we write rl.drawRectangleRec. This is our Raylib function. So this one wants a rectangle, so we write paddle rect, and it wants a color 50, 150, 90, 255, sort of a green color. If we now compile and run our game, we see this window here, and we see our paddle is a small thing up in the corner here. You might have wondered why the number 260 here. What's up with that? Well, what I want actually is for the game to sort of be 320 by 320 pixels big. But as you see, the window I've created is 1280 by 1280. If I created a window 320 by 320, the game would be very tiny on your screen. In fact, I can show you that. I mean, if you type 320 by 320 like this, then all you have is this tiny window. You can do like that if you want to, but what I'm going to do instead is use a bigger window, but then scale things up. And we're going to scale these things up using a camera. So if we switch back to 1280 by 1280 window, and then we can instead introduce a camera here. First we need to know like how big should the game be, and like I said, the expected screen size for me is 320 by 320 pixels. So I create a new constant up here called screen size. So just below clear background here, I type camera equals rl.camera2d. This creates a new variable that is a 2D camera. And the only thing, like this camera has like an offset, a rotation, a target, and a zoom. None of these really matter because I just want to use this camera for zooming up my game. So in our case, we will just set the zoom field of this camera. So I write zoom : and then I write rl.getScreen height, some parentheses, divided by screen size. So what this means is that since this value here is 1280 and this value is 320, this means that this would be a value bigger than 0. In fact, this value would be exactly 4 because you can fit 320 into 1280 4 times. So that means the game will be zoomed up 4 times. So now we just need to use this camera. So just below here, below the camera variable creation line, we can write begin mode 2D camera. And then just before end drawing here, we can write rl.end mode 2D. This means that everything that goes between begin mode 2D and end mode 2D that uses the Raylib drawing stuff will use this 2D camera to look into the world. If we now try to compile this, there is a compilation error. So rl.getScreenHeight returns a value of I32. That's an 32-bit integer. It can only contain whole numbers. If we look at camera 2D, and I can press F12 here to jump to that in the Raylib source, and this camera 2D thing here is a struct that has 4 different fields, and the zoom field has the type F32. In Odin, you need to be explicit when you convert types from one type to another, even though there is a valid conversion to do so, just so that you don't get subtle bugs from automatic conversions. So the only thing you need to do here is to type F32, some parentheses, and then at the end of this line you put another parentheses. And then if you compile and run your game, you will see this. Now it's properly zoomed up like I wanted it. So the next step is to make it possible to control this sort of paddle thingy. And we will do that by having it so that you can press the left and right arrow keys to move it back and forth on the screen. So first I will add one more constant called paddle speed. And I set this speed to be 200. What I mean by 200 here is actually that that's how many pixels per second I want it to travel at. So in 1 second it will travel 200 pixels on the screen, which is slightly more than halfway across the 320 pixels. And then I want to, inside the main game loop here, just before we begin drawing, I will put in my code for controlling the paddle. The reason I put it before I start drawing is that I want the drawing code to sort of be separate from the sort of gameplay logic code, so that drawing only does drawing. It doesn't change how the game behaves as it is drawing it. And you might see in many game engines that there is a separate sort of update and render function or something. And this is sort of similar to that. Down here is our drawing stuff. And before begin drawing here, I will do all my gameplay logic. So first let's create a variable here called paddle move velocity. And it is of type F32. And this one I will set when you press the left or the right arrow key. And I will set it to the paddle speed when that happens. So we can check if the left arrow key is held by typing if rl.is key down and then some parentheses, and then in all caps we type left like this, and then some curly braces. So if the left keyboard key is held down, then we write paddle move velocity minus equals paddle speed. And this, this variable here is 0 by default, but here we subtract from it paddle speed. So if the left key is held, then it will be minus 200. And if the right key is then held, which is if is key down dot right like this, then we do paddle move velocity plus equals paddle speed. So here you can see sort of why I put minus equals and plus equals. I could do equals equals and minus here. This would have almost the same effect. But in this case, if I hold down both keys at the same time, then first it checks if the left key is held down, and then it becomes minus 200. And if the right key is also held down, then it becomes plus 200. So if you hold left and right key at the same time and you do like this, then it will go to the right. In this case, where you use minus equals and plus equals, it will first, if you hold both, it will first go minus 200, and then it will add 200 to that, so it will be at 0 again. And then just after that, I want to update our paddle position x. So I will write paddle pos x plus equals, and then I write the paddle move velocity times dt. dt doesn't exist. By dt I mean the delta time, how long the previous frame of the game was. But like I said, it doesn't exist. So I will just actually create it at the top here. dt colon equals rl.getFrameTime. There is a procedure in Raylib that returns the frame time. And what it is measuring is actually how long it took between the last call to end drawing to the next one. So it's just the difference between each end drawing call. And on a computer, how long a frame is depends on how fast the game is running, what's like in our case, so maybe VSync is on, but screens have differently fast update rate. So this makes it so that this always updates at the same speed. So like I said before, this will be maybe if I hold the key, the right key, it will be 200, this velocity. Since the velocity is in sort of pixels per second and you multiply it by a time, then you just get a number of pixels. So sort of the units there sort of make sense. If we just run this now, then you can move left and right the paddle, but you can move outside the screen like this. So we'll fix that by just clamping the paddle position. So we will write paddle pos x equals, and then write clamp, and then we write paddle pos x 0 screen size minus paddle width. So what this clamp thing does here is that it takes the value we send in here and makes sure that it lies between this value and this value. We put 0 because all rectangles have their sort of position in the upper left corner. So at x position 0, which is the left side of the screen here, that's the minimum sort of x position we want the paddle to be able to have. So now if I move and try to move off the screen, it's no longer possible. And I can't also move anymore to the side of the screen. And this is because we don't want our paddle to stick outside. If we just typed screen size here without the minus paddle width, then the left-hand side of the paddle would be able to go all the way to the edge of the screen here, but we want the right side of the paddle to not be able to go outside. So therefore we sort of subtract the whole width of the paddle. This means that this left-hand side of the paddle is not allowed to go beyond sort of this imaginary line here. That's the screen size minus the width of the paddle itself. And then we just set paddle pos x to whatever value this clamp thingy returns. Now, I don't love that this paddle starts on the left like this. I want it to start in the middle. So let's just address that now. So what I will do is I will create a new procedure called restart. We will, for the time being, only use this restart procedure when we start up the game, but later we can use it for when you actually get sort of game over and you need to restart the game again to sort of reset some variables to good values. So just like the main proc here, I can create a new procedure here called restart : proc, some parentheses and some curly braces. And inside this proc, I will type paddle position x equals, and then I need to figure out a way to put the paddle at the middle of the screen. So what do we want to type here? Well, the screen is 320 pixels wide, and we want to put the paddle at the center like this, and the paddle itself is 50 pixels wide. And the x position of the paddle is wherever this side of the paddle is. So what we need to do here is to take this number, the width of the screen, and divide that in 2, and then we get to sort of this line here. And after that we need to get to over here, and from here to here we see that it is sort of like half a paddle width. So we actually need to take this 320 divided by 2 and subtract half the paddle width to end up at this line here. So with that in mind, we type screen size divided by 2 minus paddle width divided by 2. Now we just need to use this restart procedure. So we write it here, restart, with some parentheses like this. So this line here calls this procedure, and we do that just before the sort of main loop starts. So if we now run the game, then we see that the paddle starts at the middle instead. So let's move on to step 3 now, ball, draw and move. So we want to add in a ball that can move around and sort of bounce off the paddle and bounce around in the game, hit blocks and hit the walls and all that. We will start by just drawing it and moving it with a velocity. So we again need some variables and constants to do this. And I will start off with ball pos, the ball position. And this one is not just an F32 because it's a 2-dimensional number. It's both where on the screen vertically and horizontally is the ball, and that is best represented using a 2-dimensional vector. So we give this the type rl.vector2, and rl.vector2 is simply just 2 F32s combined together, so it has sort of like an X and a Y part. Then we need a direction for the ball, in which direction is the ball currently heading. So we write ball dir, and it's also a vector 2, since it also needs to know the X and the Y direction it's heading in. And then we need 2 constants, one for how fast the ball travels and one for how big it is. So the first one we call ball speed, which I will give the value 260 pixels per second. And then we'll also add in ball radius. And this is the radius in pixels of the circular ball. And I will give that the value of 4 pixels. So the diameter of the whole ball will then be 8 pixels. And then also actually one more constant. I want ball start Y. And that's the Y position of where the ball should start on the screen. And we will give that the value 160. Let's first in restart here set where on the screen the ball should be when it starts. So we have ball pos, we give that the value, and since, like I said, this is a vector 2, it contains 2 values, then you set both values at the same time by putting a curly brace and then separating the values with a comma. So the first part is the X position, the sort of horizontal part of this position, and for that one I want to put screen size divided by 2, so it is in the middle of the screen. Note here that rectangles count their position from the upper left corner of the rectangle, while a circle that I will use for the ball counts its position from the middle of the circle. The Y part of this position, I want to be just ball start Y, which is 160 up here. Let's now draw the ball. I always find that it's easier to, first you just give something a position, draw it, and then you can try to put in the code to move the thing around. And we will draw the ball down here. Just after we draw the paddle, we write rl.draw circle v, and draw circle v expects the center as a vector 2, we have that, that's ball position, and then it expects a radius, that's ball radius, and then it wants a color, and as usual I have figured out some kind of color here that I think is suitable. So this is a slightly reddish color. So if we now compile and run the game, you see that there is a ball hovering up here. So what I want to do here is for the game to wait for you to press the space bar, and when you press space bar, the ball starts moving. So we need a variable to know if the game sort of has started or not. So I will just add a variable called started of type bool. I will also set started in restart here to started to false. It will have the default value false, but if we later call restart when you get game over and such, it will again be reset to false. And then what I will do is at the top of the main loop here, I will actually make sure that dt is 0 unless you have started. This means that you cannot move the paddle and stuff because it's just constantly multiplying the velocity by 0. So I will actually change this line to just be an f32. So dt is a variable of type f32, which has the value 0 by default. And if we haven't started the game, so what I will do in that case is that I type if rl.is key pressed dot space, some curly braces, and inside here I will set the ball direction. For now I will just point it straight down. We'll give this a more interesting value soon. And 1,0 here is straight down because Raylib has a coordinate system where x goes to the right like this and y goes downward. So 0, 1 as a vector, you can think of an arrow that is pointing downwards that has the length 1. And then we just need to change started to be true. So if started is no longer false, then we can put an else here. So this is what happens if the game actually has started. Then we set dt to be rl.getFrameTime. So now time will only start after we press spacebar. However, we do not yet do anything with this ball direction. We're not moving the ball yet. So let's add in that now. So we will put this in just before the paddle move velocity variable here. We will put in ball pos plus equals ball dir times ball speed times dt. So I always expect the ball dir here to be just a direction, and the speed times the ball dir then is sort of the velocity. A velocity, in if you try to be a bit more physicsy about it, is when you combine both a direction and a speed. But keep in mind here that this direction must be sort of length 1. You see this thing here is of length 1. If it was -1, this would also be of length 1. But this is no longer of length 1. Something that points both to the left and downwards, that is of length 1, is something like this, I think. But we will look into making sure that the ball dir is always of length 1 a bit later. So if we now start the game, then the ball is there, and if we press space, then just falls down, goes through the paddle because there's no collision yet, and disappears. In my version of Breakout, I think it would be fun if the ball is sort of, before you start the game, it's sort of moving back and forth, left to right, and then when you press space, it launches towards the paddle. So you can sort of choose the angle of how the ball hits the paddle from the start. So just inside here, we haven't started the game, but we also haven't pressed space yet. Then we write ball pos equals some curly braces, so we set the value of the ball position each frame here. And we can then type screen size divided by 2, that's the middle of the screen. And then we need to have some way to sort of vary the position of it over time, so it just sort of goes back and forth like this. And you can do that using a mathematical function known as cosine. And cosine varies between the values -1 and 1 depending on what sort of values you feed into it. And you might recognize this cosine thing from trigonometry or something, where you used it to calculate angles in triangles and stuff. And we can fetch this cosine thing by importing the maths package from the Odin core library. So we go to the top here, and just below import RL vendor Raylib, we type import core : math. So if we go down here again, now we can type math.cos, and we type a parenthesis, but now you need to feed a value into math.cos. And what we want here is that we want to feed the current time, which is for how long has the game been running, and we can fetch that from Raylib by typing rl.game getTime. Notice that this is getTime, down here is getFrameTime. This is how long the previous frame was. This is how many seconds has elapsed since the game started. If you just compile this now, then there's one problem, that rl.getTime returns an F64, which is a decimal number of higher precision than F32, and bool.pos expects F32 numbers. My advice is to don't put the cast in here. Don't do like that, because math.cos will return a value between -1 and 1. That's perfectly fine to cast F32, but rl.getTime will, continuously grow. So maybe you want that precision of your 64-bit floating point number there. So put the cast outside here instead, which will be much better. If you now, and then of course that's not all we need. We also need the Y position of where the ball should start. So we type ball start Y. If we now compile this, then nothing seems to really happen. But if you look really close, the ball is actually moving a tiny bit here. But like I said here, this cos thing just varies between the values -1 and 1. So it just sort of wiggles at the center, because we take the screen size divided by 2, the center of the screen, and then sort of wiggle around the middle there. But a nice thing we can do here is just to multiply whatever comes out here by something. And so if we multiply by 20, then it will go between -20 and 20, for example. In our case, we want it to almost go to the edge of the screen, but not really. We know that that means we almost want it to go half a screen size away from the middle. Half a screen size is screen size divided by 2. So we want something slightly less than that, so it doesn't go all the way over there. So what I will do is just before the last parenthesis here, I will type times screen size divided by 2.5. So now if you run that, you see that the ball is sort of wandering back and forth like that. But currently if you press space, it still falls straight down. I want it to fire towards the paddle. And the way we will make it travel towards the paddle is by changing the direction of the ball when the game starts. So instead of this stuff here, we will calculate ball there to be a vector of length 1 that points from the ball position towards the middle of the paddle. So let's first calculate what is the middle of the paddle. Well, paddle middle is an rl.vector2. The x part of this is just paddle pos x plus paddle width divided by 2. Now remember, paddle pos x is just the left hand side of the paddle, but we want the middle here. So what we will do is we will take the left hand side and then we'll add half the width, which will make us end up sort of there. And then we type paddle pos y. So that's the middle of the paddle. So then we need the vector that points from the ball to the middle of the paddle, and I will call that ball to paddle. And this one I will give the value paddle middle minus ball pos. So one thing to notice here is that when you want a vector to go from a position to another position, such as from ball pos to paddle middle, then you type paddle middle minus ball pos. So this is where it goes from, and it goes to this point. So in our case, we go from the ball to the middle of the paddle. If you reverse the order here, then you get a vector that goes from the paddle to the ball, but we want to calculate the direction in which the ball should travel. So this is what we want. However, this ball to paddle thingy won't have length 1. Like I said before, we only want the speed to be governed by the bold speed thingy here, and we want this thing to always be of length 1. So regardless of what we choose, which direction we choose here, the ball travels at the same speed. Making a vector length 1 is known as normalization. And we have some built-in procedures for doing normalization in Odin, and those you find inside the linear algebra package. So we can go to the top here and import that. Import core:/linalg. So we go back down here now. Then we can replace this thing here with linalg.normalize 0 ball to paddle. There are two versions of normalize. The one without a 0 gets an error if this vector is of length 0. But in our case we use the one with 0 here, which will just check if it is 0, then it returns 0, which is a bit safer. So if we now run this and press space, then we see that the ball sort of shoots towards the middle of the paddle, which is what we wanted. So let's now move on to step 4, collision with paddle and walls. This means that we want the ball to sort of collide with the paddle and the walls and bounce around a bit. We will start with the collision with paddle part. We will do this by checking if the ball is somehow inside the paddle, and then we will figure out which direction to bounce it after that. So what we will do here is down here, after we move the paddle, we will do the collision check between the ball and the paddle. And we need to have the paddle rectangle to check the sort of the ball against. And we have the paddle rectangle down here. So let's just take this rectangle stuff down here, cut it and move it up to here, paste it in there instead, so we can use it a bit earlier. Because like I said, I don't want to put gameplay logic down here in the drawing code. I want to keep it before the begin drawing stuff here. And we'll do the collision check between the ball and the paddle rect by typing if rl.check collision, and then I will look for the different version of check collision here, and we want the one called circle rec, check collision circle rec. That one takes a circle and a rectangle and checks if they overlap somehow. So this one wants a center point of the circle, that's the ball position. It wants to know how big is the ball, that's the ball radius. And it wants to know which rectangle, that's the paddle rect. If this procedure returns true, then these two are somehow overlapping. So what I will do here is, if the ball comes in towards the paddle like this and hits it, then it's sort of overlapping like this. And then at that point I want the direction the ball travels to sort of be reflected and sort of bounce away like this. So we need to figure out sort of how to bounce this ball away somehow. The way we will do this is by using a linear algebra procedure called reflect. And reflect wants to know which vector, that is the ball direction, do you want to reflect, and what's the sort of plane you want to reflect it against. So what this means is that if you, for example, come here and hit the top, then the plane is this plane. And it describes this plane by a normal. A normal is which direction does this sort of surface point. And this top of the paddle here points upwards, right? So that means that we will take the ball direction, which comes like this, and we will reflect it on this line here, which has the normal pointing upwards, and then it will sort of bounce off in that direction. So we need to figure out this collision normal. So I will type collision normal is an rl.vector2 in here. And what I will do here is I will, since I know that the ball is overlapping with the paddle right now, the center of the ball might not be inside it yet because the ball has sort of a size. But just to make sure that I use a value that's guaranteed not inside the paddle yet, I will use the previous ball position. So up here I will type previous ball position pos equals ball pos. So before I change the ball position, I store the previous ball position like this. So then down here I can check if the previous ball position dot y is less than the paddle rect dot y plus the paddle rect dot height. This means that the position of the ball the previous frame maybe was here, and then after that it traveled here and collided. But then I can see that, okay, it was somewhere above this line. That's the Y position of the paddle plus the height is sort of this line here. The previous frame, the ball was sort of somewhere above this line. In that case, I want to add to the collision normal. So the collision normal will be used for doing this reflection I talked about. So in that case, we add 0 minus 1, which means that we add a vector pointing straight up. And then we also want to make sure to push the ball out of collision. So we say ball pos.y equals paddle rect.y minus ball radius. Because if we just type like this, then we are forcing the ball to sit like this with the center of it at the top of the paddle rect. But what we want is it to sit like this. So that's the one radius away from the top of the rectangle like that. So that's why we are subtracting the ball radius here. So it goes upwards by 1 radius. Then we can add in a case for if we hit the paddle from the underside. This is quite unlikely, but we can just push change the collision normal to point downwards in that case. So if the previous ball position of y was bigger than paddle rect of y plus paddle rect of height, then the collision normal, you add 0, 1 to that, and then you take the ball post of y equals paddle rect of y plus paddle rect of height plus ball radius. Like I said, this is quite unlikely, but if the ball comes flying like from the side like this and sort of hits here and the center of it is sort of below here, then I want it to sort of bounce off and bounce down. You will lose, of course, because it bounces out to the outside of the screen, because if you go anywhere outside the bottom of the screen, that's how you get game over. It's just sort of a more visual way to get that sort of game over state. And then if during the previous frame the ball came from the side like this, if the previous X position of the ball was over here, then I also want the ball to sort of bounce a bit sideways. So in that case I can say if previous ball pos.x is less than paddle rect.x, this is actually for the left side, so over here. So if the ball was over here and then intersected the next frame maybe like this, then I want it to get also a direction to the left. So in that case I take collision normal plus equals -1, 0. And then I also want to check if I collided, if I was the previous frame on the right hand side. So if previous ball post.x is bigger than paddle rect.x plus paddle rect.width, then the collision normal, we add 1, 0 to it. So maybe now you can see like we actually we almost always add this part, so it bounces upwards. Then if you also came sort of from the side, then we add the minus or the +1 to the X part of it. So it will, in most cases, just point straight up, except in some cases it will also point to the side. Now, again, this vector, in this case, it is of length 1. If you hit from the side like this, then it will no longer be of length 1. So what we will do here is that we will write if collision normal is not 0. This is just a little safety check. Something has gone horribly wrong if it is 0 here. In that case, we set the ball direction to linear algebra.reflect. This is the procedure in linalg I talked about that reflects things. And we take the incoming angle, which is the ball direction, and we take the normal, which is the collision normal. However, you should not use it straight up like this, because reflect assumes that this is of length 1. So you should do linalg.normalize. Before I use normalize 0, now I know that this one isn't 0 because I check here, so I can just use the normal one. And then finally, we actually need another normalization here because this reflect might not be 100% numerically sort of, it might return something slightly longer or slightly shorter in some cases. So I would just put in linalg.normalize again here. So if we now do that and try to play this, then we have our ball going like this and we launch it and it bounces off the paddle and disappears forever. So now it would be nice if we could make the ball collide with the left wall, the top wall and the right wall. But like I said, the bottom wall is for sort of the game over state of the game. And the way we'll do this bouncing is that we will check if the ball is outside or partially outside the left or the right or the top side of the screen. So let's start with the right hand side of the screen. We check if ballPos.x plus ball radius is bigger than screen size. This means that the ball is like this. The ball might be here, but the x position plus the radius is more than the width of the screen. In that case, we say that the ballPos.x is screen size minus ball radius. This just sort of forces the ball back so it is completely within the play area again. And then once again, we want to reflect the ball direction to make it bounce on this side of the screen. So we can do something similar to what we did with the paddle down here. So we type ball_dir equals linalg.normalize, and then we write linalg.reflect. And we want to reflect the direction of the ball, and the normal we want to use is this wall here. This wall here has the normal that points straight to the left. That means -1, 0. So we just type rl.vector2 -1, 0. You can't just skip vector2 here because this procedure can get confused which type you mean. In some cases you can skip the type here if there's only one version of reflect that always takes a vector2, but in this case it's a bit more generic than that. So in this case you must specify which one you want. So if you would now play the game and you would hit the right hand side of the screen, then the ball bounces away. But as we see, we haven't fixed the top or the left yet, so let's do that. But before we do that, something you might notice here is that this stuff here and this stuff here is quite lengthy. So let's just put that into a separate procedure that we call reflect that does these normalizations and stuff. So I will take this line, copy it, and then I will go to the top here. So reflect is a procedure that takes a direction and a normal, and both are of type rl.vector2, and it returns, and you put the return value after this arrow like this, rl.vector2. And then I paste my stuff into here. I think I'm gonna take this stuff here, break into a new line, and I will call this new direction is we reflect in the direction using the normal, and then we return the normalized value of new direction. You might notice here that we wrote a comma here. You could have written like this, normal : rl.vector2. However, if you have multiple parameters to a procedure of the same type, then you can put both together like this and just type the type once. So now we can go back down here and we can type ball_dir is reflect ball_dir, and let me just mark all this stuff and delete it. You see, now we do not need before this we had this explicit rl.vector2 here. In this case we do not need it since it can see on the parameter here that it expects a vector2. And then down here as well we can write ball_dir equals reflect ball_dir, and we want to reflect in the collision normal. So let's add the top and left parts now of the wall collision. So for the left wall on the screen, we can type if ball_pos.x minus ball radius is less than 0. So what this means is that if the ball is over here and the center is here, then we take the center, the x position of the center, subtract the radius, and then we end up on less than 0, because this line here, the left-hand side of the screen, is x equals 0. So in that case, we say ball_pos.x equals, and then we can say ball radius, because it's like this is like, you know, 0 plus ball radius, but just type ball radius instead. And then we write ball there equals reflect ball there, and then the normal now is 1, 0, because this is a wall that's pointing to the right on the screen. And finally, let's add in the top. So we write if ball_pos.y minus ball radius is less than 0. And this is just similar thinking to up here, but in the y position instead, since the top of the screen is at y equals 0. In that case, we said ball_pos.y equals ball radius, and then we said ball there equals reflect ball there, and we reflect in which vector, in which normal? Well, it's pointing downwards, since it's the top. So now, if we do this, we can play this useless game where it just bounces around. Finally, when the ball falls out the bottom here, we will just restart the game. We'll add some nicer sort of game over screen later, but for now we can just restart the game when that happens. So the way we do that is by typing if ball_pos.y is bigger than screen size plus ball radius times 6, for example. I put this in here because ball_pos.y is the middle of the ball, and I want to check if it has just disappeared sufficiently past the screen size, so it's completely outside it. And in that case, so that's why I type times 6 here. It's just a number. It could be times 10, times 5, it doesn't matter. But in that case, I run restart. So now, if it falls outside, then the game starts over. So let's now add in some blocks that are up here, sort of some small blocks that you can hit with your ball, and when you hit them you'll get points and stuff, and the blocks will have different colors. All that stuff that you see in Breakout and Arkanoid style games. So we will add the blocks by adding in two constants called numBlocksX, which I set to 10, and numBlocksY, which I set to 8. And what this means is that I want, in this, I want sort of like this, and I want 10 blocks. Imagine this is 10, probably isn't 10, and then I want 8 rows. So I'll have 10 sort of columns, and then I have 8 sort of rows like this of blocks. That's what I want. So now I also need some way to know if a block still exists, if it hasn't been hit by the ball and has been sort of destroyed. And I will keep that information in a two-dimensional array called blocks. So I will type blocks : and then I will type one bracket like this, and I write numBlocksX, and I type another bracket like that, and I type numBlocksY, and then I type bool here. This is a two-dimensional array that is 10 by 8 big, and it contains bools, like a series of bools. It's essentially 80 bools, but you can use sort of an X and a Y position to identify them. Then inside restart here, we will initialize the blocks so that all of them have the value true. So I write for X in 0 ... less than numBlocksX, and then I write for Y in 0 ... less than numBlocksY. This kind of loop just says that make a loop where there is a loop variable called X and step through all the values from 0 up until numBlocksX minus 1. So this one will go from 0 to 9, and this one will go, Y will be from 0 to 7. So here I can type blocks X y equals true. So we just go through all of them and sets each value to true. Let's now draw our blocks, and we will first draw them just white, and then after that we will add some color to them and stuff. So we go all the way down here, and down here just after we draw the ball, I will make one loop for x in same as before, 0 to num blocks x, and then another loop for y in 0 to num blocks y. And if the block at that position doesn't exist, which means that if you fetch with this x and the y, the block there, and it says false, because it's just a bool on each one, remember, then we just write continue. This will make it skip this lap of this loop so that it goes to the next one, so we don't draw that one. Now we need to create a rectangle for this block. I actually need to add in some more constants for that, I realize. So we need a block width, which I choose to be 28, and we need a block height, which I choose to be 10. So we can now create a rectangle that represents this block. So we say block rect. We make a new little variable here called block rect. It is a rectangle. The x position of this rectangle I want to be, and I cast it to an F32 here because x here is an integer. So I just write 20 plus x times block width. Block width I wrote was 28 up there, and I write 20 plus 20 here. This is just so that you get a bit of padding on the side. I have actually chosen this block width of 28 so that with a screen size of 320, if you add 20 on the side and you have 10 blocks that are each 28 pixels wide, then you get 20 pixels on each side if you just add it on here. So that's why it's like that. So, and then we need a y position, and I say 40 plus y times block height. All the blocks start 40 down from the top of the screen. And then each block is block width wide and block height high. And now we can draw this rectangle. rl.draw rectangle rec block rect. First, let's just draw it white. So we compile and run it. So now you see that this is this big, this is just this giant block up here, but this is actually 10 by 8 blocks that are just drawn all in white. So we now need to give these blocks different colors and stuff to make them stand out a bit more. We will do that by going to the top here, and here I will create an enum called block color. So this enum will be used to identify the different colors a block could be. And the different colors I have chosen are yellow, green, orange, and red. And enums are essentially just a way to associate a name with a number, where yellow is 0, this is 1, 2, and 3. Now I need to choose which color should each row of blocks be. So the way I will do that is by writing row colors. And here I make a fixed size array, and the size of this array will be num blocks y, because that's how many rows there are. And it will contain block color values, which is this enum up here. So I will just choose for each row which of these 4 values to use. And what I will do is I will just put in 8 values here, so that the top 2 rows are red, and the next 2 are orange, and the next 2 are green, and the bottom ones are yellow. Oh, it's a bit upset here because I was supposed to type num blocks y. And you see this dot here is, I can type block color dot red, but since it knows the type of this array is block color, I can implicitly choose that by just having the dot there instead. So it just implicitly puts this in the enum type for me. So now I've chosen which color should each row be. Now I just need to say, like I said, yellow, green, and orange here, but I haven't been more specific which colors those actually are. So now I just need to say, what does yellow mean? So then I say block color values is a array, and here I will type block color, and the type of each element in this array will be rl.color. This type of array is slightly different to this one. This one is a fixed size array. This one just says, okay, this one is 8, like this is the same as writing this. It has 8 values. However, down here we type an enum here. This is called an enumerated array. And this type of array will be as long as there are a number of elements in this enum. And for initializing it, you have two choices. Either you leave everything zeroed, or you have to type in all the different enum values. So in this case, I have to type yellow equals and then a color. So I write yellow equals 253, 1249, 150, 255. This is just the yellow color I have chosen. And then I type green equals 180, 245, 190, 255. I have this noted on the side here, and I'm not an oracle of making up colors. So the orange is 170, 120, 250, 255. That's not really orange, is it? I think it's a typo. This is more of a purple color actually, but that will have to do for now. And then finally the red one is 250, 90, 85, 255. The nice thing here with enumerated arrays is that if I were to add another color here, actually called purple, then I would get a compilation error until I add it here, the line for it here. So that way you can sort of force yourself to have a mapping between an enum and use an array to sort of store different values connected to each of those enum values. Okay, so now we have our colors and stuff here. So let's now go back down and use these colors to for our blocks. So what we can do here now is instead of rl.white, we can just say fetch the block color value, and this one expects an enum, and we can get an enum by writing row colors y, because y goes between 0 and 8. Row colors gives me an enum value for each of those rows, and then we use that to fetch one of those colors. So if we now run this, you will have these nice colors like this. And yeah, like you see, the orange is actually purple, but yeah, you can change that name yourself if you want to. The blocks are still hard to make out because they don't have any kind of border. They just sit next to each other. So I want to add in a little border. So I want to just draw a border around each block like this. And to draw that border, I will use sort of a line drawing procedure in Raylib. And then I need to know like what's the top left corner, the top right corner, the bottom left corner, and the bottom right corner of each block. So let's just write down those corners first. So top left is an rl.vector2. This is the top left corner. This is just block rect.x, block rect.y. The top right corner is an rl.vector2. It's at block rect.x plus block rect.width. And this hopefully makes sense since the x position is here and the width is like this. So we're trying to get to this position. So we add the width of the thing. And then the y position is just block rect.y. The bottom left is rl.vector2. The x position is block rect.x since we're at the left side again. But now we need to go to the bottom of the rect, bottom of the rect like this. Block rect.height. Same thinking. We want to get here, so we add the height to sort of get to down here. And then finally we need bottom right. It's an rl.vector2 block, and this one just combines it all. It's just block rect.x plus block rect.width, comma block rect.y plus block rect.height. And now we'll just use these four corners to draw lines along the sides. So we'll draw first one line, rl.drawLine, use draw line ex because that one gives us a start, and a line thickness and a color. So we start at the top left and we go to the top right, and we want it to be one thick. And the color I have just chosen to be 255, 255, 150, 100. It's sort of like a gray and it's not fully transparent. So some of the color behind it that comes from the rectangle that is drawn behind that is colored. sort of shines through. So if we look at this now, then we see that there's a line on top of all these now. We can then just copy this line, and we go from top left to bottom left. That should give us the side like this. And now we just want to put the bottom side and the right side, and those I will give a slightly darker color, so it looks like light is sort of shining from the top left or something. So I will just copy this line here, and I will write from top right to bottom right, so that's the right side, and we use a slightly different color. We use 0, 0, 50. So this is very dark blue color, but it's also semi-transparent. And then finally we will add in the bottom, from bottom left to bottom right. So if we now look at this, it looks like this. So we see all our blocks nicely separated now. So currently, if you play the game, the ball goes straight through the blocks. Now we need some kind of collision detection with the blocks. So let's add that in. And we will add that up here, just after the ball collision check stuff here. So what we'll do is we will again loop for x in 0 to num blocks x, and for y in 0 to num blocks y. I loop again here because, like I said before, I want to keep the drawing code from the sort of gameplay logic code separated. So in here we'll do all collision checks and stuff. And just like before, we check if blocks x and y equals false. Then we continue. We just skip this loop, this lap of the loop. And now I want this block rectangle, but since there are some hard-coded values in here, I don't just want to copy it, because if I want to change this 20, then I must change it in 2 places. So let's just make a little procedure instead that does this stuff. Let's write like this. I want to call this procedure calc block rect, and I send in the x and the y. So let's just, that's the name it will have. So let's go to the top here. I cut out that stuff, and I go up here and write calc block rect is a procedure that takes an x and a y, integers, and it returns an rl.rectangle. Then I can paste that stuff in, move it a bit, and then I can just return like that. You don't need to put the type on the return value, since it figures that out from the type here. So then this stuff should work like before, but now we can use calc block rect up here as well. Block rect equals calc block rect x, y. Now, just like with when we collided with the paddle, we want to check if there's a circle inside a block. So we check if rl dot check collision rec circle with rectangle. So it's the ball position and the ball radius, and we want to compare it against the block rect. So if we end up inside here, we know that the ball is more or less touching a block. So now we will need to do a couple of different things. We will need to destroy this block, but first we need to figure out which direction should the ball bounce towards. And this is just like in the case with the paddle. So we write a collision normal is an rl.vector2, and we again use the previous frame, previous ball pos.y. So if the ball, the previous frame, was above the block rect, so if there's a block like this and your ball was up here the previous frame, but now it is here, then the previous frame, it was this, the center of the ball, you know, was above the x position of the block, which is what this thing is saying. In that case, we take the collision normal and we add 0 minus 1 to it. Then we will just do similar things for all the other cases. So if you was below the block, the previous frame, so if previous ball position.y is bigger than block rect.y plus block rect.height, then we say collision normal plus equals 0, comma 1. And again, I'm using the previous ball position here because I am checking if it's outside. I can be sure that the ball was outside this block the previous frame. But during this frame, since it's colliding with it, it might have already gone all the way inside so that the middle of the ball is actually inside. So then none of these things will be true because it's not above. It's not up here, it's not up here, it's not over here, it's not over here. It's inside the thing now already. So it's hard for me, it can get buggy with figuring out the normal. So instead I use the previous frame's ball position to do that, which will always be outside it. And then we do the same for the sides. If previous ball pos.x is less than block rect.x, so you were on the left side of the block the previous frame, then we say collision normal plus equals -1 0, and then we check if previous ball pos.x is bigger than block rect.x plus block rect.width. In that case, you guessed it, collision normal plus equals 1 0, like that. And then down here we say if collision normal is not 0, then we say that the ball direction is reflected. We reflect the ball direction in the collision normal. Finally, we need to destroy this block. So we just say blocks x, y equals false. That will set that block in this two-dimensional array we have to false. Finally, I also want it to be possible to only destroy one block per frame. Sometimes maybe you somehow was able to hit 2 blocks, but I'd rather wait with destroying another block until you hit something again. So with that in mind, I want to sort of stop this whole collision check loop at that point. So one problem there is that if I just write break here, break will stop this loop, the one you're currently inside, but I actually want to stop this one out here. What you can do in order to stop the outside loop here is to give it a label. So we can just say block x loop colon, so we give this line sort of a label like this. And then we say break block x loop like that. So that will make this remove that block and break the loop. And now if we play, we can actually kind of play the game now. It removes blocks and it bounces. So there is a quite subtle bug here, and that is if the ball hits on a corner of 2 blocks like this, like say it hits just here, what will happen then is that the ball might get launched sideways even though you thought it would reflect straight down. Because if you hit a wall of blocks like this, then you just expect it to bounce sort of downwards, but it might bounce very much sideways because it sort of thought it hit the corner of a block, but it didn't really hit the corner because there are blocks to the left and to the right of it. There are a bunch of different ways to fix that. What I will do is just check if there is a block nearby, and in that case sort of remove that part of this collision normal. So I will add a small procedure called block exists, and what this procedure will do is just check if the blocks in some direction exist, and in that case I will modify the collision normal so this thing doesn't happen. So we can go up here and we write block exists, and this procedure takes 2 integers and it returns a bool. It just returns true or false. If x is less than 0 or y is less than 0 or x is bigger or equals to num blocks x or y is bigger or equals to num blocks y, then return false. That means we were outside. This block cannot possibly exist because we are outside of the whole blocks array, because x or y are negative or they're bigger than one of these 2 values. Otherwise, just return blocks x, y. So now this thing tells us if a block exists. So now we can go back down here and we can say using two if statements, one for the x direction and one for the y direction. We can say if block exists x plus, and we cast to integer because the collision normal is a float, but it is whole numbers like this. You see, there's no decimals involved in here. So we can just write collision normal.x and then comma y. So if collision normal.x is -1 or +1, then it will check to the sides here if there is a block there. And if there is a block there, then the collision normal.x should be 0. We use 0, like whatever happened here, if it added -1 or +1 to the x part of the collision normal, we just zero that out, because we don't want this sort of collision flying off to the side as if it hit a corner when there was actually a block next to it in that direction. And then we can do the same thing here. If block exists x comma y plus int collision normal.y. And then we say collision normal.y equals 0. You can see why this is a problem if you play a bit yourself without this stuff, and sometimes when you hit blocks, your ball will just go flying off in weird directions. So now we've played the game. This is kind of playable now. It's doing all the things you might expect from a game like this. Gets stuck up there for a long time, does nice stuff like that, bounces around. Yeah. Now I thought we can add a little score counter to give us scores when we hit these blocks and have some kind of way to display that on the screen. So what we will do, just at the top here where we have our global variables, we will add a new one called score. It's an integer. We'll make sure to zero that one out in restart in case you restart the game. And then we want to map each of the possible colors of blocks to a score. Like how much points do you get for that one? And the ones at top give more than the ones at the bottom. So I will add this mapping of block color to score using another one of these enumerated arrays. I will write block color score, and I type the enum value, block color, to an integer. So now I must type in how many points does yellow bring? I say 2. How many points does green bring in? That one is just above the yellow one. I say 4. How many points does the orange, that is actually purple, bring? I say 6, and the red one gives 8. So now we can, each time we hit a block, we can give you some points. So let's go back down to our collision code where we destroy the blocks and all that stuff. Here is where we can increase the score. So we fetch the color of the row color, by doing row colors y. And then we add to the score by doing score plus equals block color score row color. That will increase our score. Now currently there's nothing that displays the score on the screen, so we need to add that before we can kind of test this. So what we will do is we'll go to the bottom here, and just before end mode 2D here, we will add in sort of our UI stuff with where we'll put all our text sort of down here. And we need to convert this integer score into a string that can be displayed on the screen. So we will type score text equals fmt.ctprint score. And then I will write rl.drawText score text, and this draw text wants a string, and then it wants a position, x, y, a font size, and a color. So I will say 5. That's 5 from the side of the screen, 5 from the top of the screen, 10 pixels high, and white text. Now the FMT package here is not included yet, so we will import it up here. Import core FMT. Let me just say a few things about these things here. So this thing takes sort of any variable here and tries to create a string that represents that, whatever that one contains. In this case, it will make a string that contains the numbers that this integer score contains. In this case, since Raylib is written in C, it actually wants a C string That's why there is a C here. You can create Odin strings from like this, but if you put a C there, then you get a C string. That's one thing. Now, the T here stands for temporary. Odin is a manually memory managed language, and when you do something like this, you need to allocate memory for your string so that you can put the, for example, score into it. But in order to make life a bit easier, Odin provides a temporary allocator, which is for temporary things that we do not need in the long run. So this thing here will make it create a string from the score using the temp allocator. However, the temp allocator, we need to tell it at some point in our program that I don't care about any of the memory allocated using the temp allocator anymore, please throw it away. So that you do by writing something like this: free all context.temp allocator. I write this line here. This is the last line of the main loop. So this loop goes on and on and on. So what this means is that anything that is allocated on the temp allocator is valid until the end of the frame. That's what this means. So you can just use this to allocate memory without having to worry about when that allocation is going to be freed and stuff. Now if you compile and run this, you get a compiler error. Undeclared name, block color score. I have up here accidentally typed a capital K here. So if we now compile and run, we see that we have a 0 up here, and if we hit some blocks, then we see that quickly grew as the ball went up there. Now, whenever you get sort of game over, it would be nice if currently the game sort of just resets instantly. It would be nice if you could sort of see your score for a while and then press a button to reset the game. So let's do that. What we'll do is we will here, just below started, we will add another bool called game over. And then where we reset the game here, instead of resetting it, we will just say game over equals true. I will also just check so game over isn't true here, because I will play a sound here later. I don't want it to loop over and over again. And then we can go up here. So we have this case: if the game hasn't started, then we do this. Let's add in another one: else if game over. We do some stuff. If the game is over, I also don't want the time to sort of tick. But the only thing I want to do here logic-wise is that I want to check if rl.isKeyPressed .space, then and now I reset. So if I now play the game, we get some score, and now the game is stuck until I press space. So let's add some text on the screen that says game over and how much score you got in the middle here. So again, we'll go to the bottom here to add in our text, and what we will do is just here we will type if game over. Then I write game over text, and here we use fmt.ctprint, and we say score v like that, reset, and then we say use the space key score. What this stuff means is that you see there's a difference here. Here we have F, here we didn't have F. F lets you provide a format string, so I can type a string here and then I can type this %v here and a couple of different values. So I will have this is the string I have, and it will replace the %v with this one. So it will say score and the number, and then it will say this stuff here. I want to place this text on the middle of the screen. In order to do that, I must know how big this text is. So I can use Raylib to calculate the text size. So I will say game over text width is rl.measure text, and then I say game over text, and then I say 15. This is the size I will use when I draw it in the next line, but yeah, just so you know. And then I can write draw text, and now it wants me to provide the text I want to draw, and then it wants the X position. So in order to center something, just like when we centered the paddle at the start, we take the middle of the screen and then we subtract half the width of the thing we're trying to center. So we say screen size divided by 2 minus game over text width divided by 2. For the Y position, I want it to be sort of slightly above where the ball starts. So I just say ball start Y minus 30. I want this text to be 15 pixels high and I want it to be white. So if I now run this and I get game over, then it says score 2, reset, colon space. And then you see there's a bug here because I do not reset the game over flag when I run restart. So we can go up and do that. Restart. Here, game over equals false. Finally, I also want there, when you start the game, it's not obvious that you need to press space to start to kind of launch the ball. So let's just add a similar thing here. If not started, then we'll do some stuff. I can probably copy this stuff here, and then I say just start space. Then I do not need the format string since there's no score there, and we call this one, you can press Control D to expand your selection like this, then you can write start text like that. So start text is this, and then it measures it, and then it places it like that. So now if you start the game, it says start space, and then it disappears, and then you get to here, and then you're back here again. Okay, now I want to add some graphics. I have, in the description of this video, there is a zip linked. This zip contains 2 pictures and 3 sounds. So we will now put in some graphics for the paddle and the ball, and we'll add in 3 sounds, sort of sound effects for when things happen in the game. So when you have downloaded the zip, put the contents of the zip, which is these 2 images and these 3 sounds here, put them next to your breakout.odin file. So, because that's also where the exe ends up when we run the Odin compiler, so that the exe can find these files and load them. So let's start with the graphics. In order to use these graphics, the first thing we need to do is load some textures. So we go up here to the top. So here we will first load the textures we need so that we can use them in the main loop later. So I will first load the ball texture. Ball texture colon equals rl.load texture, and it's called ball png. Then I need a paddle texture. And then we use rl.load texture paddle.png. And now we need to go down to where we draw those circles and rectangles for the ball and the paddle and replace those with these textures. These 2 lines is what we will need to replace. So let's start with replacing the paddle drawing. So we write rl.draw texture v. Draw texture v first wants a texture, that's the paddle texture. Then it wants a position. We have the x position, so we can just construct a vector inline like this. We write paddle pos x, and then the paddle's y position is that constant paddle pos y. And then the tint should be rl.white. Like the color we send in here is just for sort of recoloring the texture. It's not for it. If you do not want to recolor it, you just send in white. If we now play this, then we see that the paddle now has this new fancy look. Now let's replace how the ball looks as well. So we'll do rl.draw texture v, and we will draw the ball texture at the ball position. Here there is a slight difference because draw texture v wants to know where is the upper left corner of the thing you want to draw, sort of like a rectangle, but the circle we drew here has the sort of position in the middle of the circle. This ball texture is 8 by 8 pixels big, so we need to sort of subtract a bit from it to make it end up at the center of this ball. So what we need to do is just actually to subtract ball radius. So we subtract from this vector this other vector that is 4 by 4, just so it ends up at the middle of this position instead of the top left corner. And then we color it white as well. And now you see that you have this new fancy ball as well. So let's now add in some sounds for one sound for when the paddle is hit, one sound for when it's game over, and one sound for when the ball hits a block. In order to use sounds, the first thing you need to do is to initialize the audio device. This is sort of similar, to initializing the window here. You also need to tell it that you want to use sound. So you just write rl.init audio device like that. And then, just like there is a close window at the bottom here, you can also do rl.close audio device. So now you are ready to play audio. First we need to load our sound effects, just like we loaded textures. So we'll make the hit block sound is rl.load sound hit block.wav. And then we need the hit paddle sound. It is rl.load sound hit paddle.wav. And then there is the game over sound, which is rl.load sound game over.wav. Now we just need to play these sounds in appropriate locations of the game. I will start with the hit paddle sound. Paddle happens when the ball collides with the paddle rect. So we can do it down here. rl.play sound hit paddle sound. You can test this, start the game. And as you hear, there is sort of a funny noise. Now we can add in the game over sound, and that happens up here. So we can just type here rl.play sound game over sound. And this is sort of why I added in this little check here, because if you don't have this, then it will actually each frame end up in here over and over, since the ball continues to be outside the bottom of the screen. So it will make a lot of noise. So now if you do that, then there's some sound. Now let's add the sound for when you hit a block. And for this one, I also want to add in some pitch shifting so that it sounds a bit different each time, because you will hear that sound over and over and over again. So we can do that down here. We say rl.play sound hit block sound. We can just first try without the pitch shift. Yeah, it's the same sound played over and over. So let's add in a slightly random pitch shift. In order to use sort of random stuff, you can import the random package in Odin. So you can scroll to the top here and write import core math/rand. And then you spell correctly also. Import core math/rand. So now down here you can say rl.set sound pitch. And then you set the pitch of your hit block sound, and pitch 1 is the default. That's how it sounded when we're playing right now. So I want to pick a random value between 0.8 and 1.2. That will give a slight variation. So we say rand.f32 range like this. And this one just wants the lowest value and the highest value like this. And now if we play, there's a slight variation each time you hit the blocks. So let's now move into fixed time step physics. And this will be a sort of little treat here at the end where I talk about problems with how we're currently doing this sort of multiplication with the dt, whenever we, for example, move the ball, we multiply by dt here, but this dt will vary in size, and if it becomes too big, then your ball might go through things and stuff. As an example, I can set the target frame rate here to 10 so that the game will go extremely slow. If I play this now, then you see the block just went straight through things, and there it went straight through my paddle as well. So So what happens here is that the frame rate is so low that if this is our block down here, then in one frame the ball is here, and in the next frame the ball is here, because it multiplies the direction the ball is traveling, which is this direction, times some speed, then times dt, which is how long the previous frame took. This stuff here. So the ball direction times the speed times dt. Now if you have 10 frames per second, that means that each frame takes 100 milliseconds. That's quite long. So if it multiplies the direction times the speed times 0.1, which is 0.1 100 milliseconds, then your position might just go straight through the thing, and then you will never be able to do the collision check with this rectangle here, because it will already have passed to the other side. You will never see it be inside it. Another funny way to see this problem is if you reset this back to 500, play the game, and you, in Raylib there is a thing where, at least on Windows, if you hold the title bar of the window, then time stops, but then the first frame after it resumes will actually get a very high dt. So if I let the ball go and then grab the window and release, then my ball has already gone through the paddle and crashed at the bottom. So what we will do here instead is that we will step the whole game at a fixed frame rate, and how many times we step it will be based on how long the previous frame was. There is this article called Fix Your Time Step that I will link in the description, where you can read about this. It's quite a good article. It can be a bit theoretical in the sense that it rather than talking about maybe simple things like position and stuff, it will talk about the state, and to some people it can seem a bit abstract maybe. So we will just do this article has several different variations of how to do this more and more properly, and we will just do the most sort of proper version here. So what we will do here is, if we look at the previous example where the ball was first here and then it went down here, sort of teleported through, instead we will do lots of tiny sub-steps, and these sub-steps will always use a fixed delta time. The dt will be fixed. So if we have if we suddenly get 100 milliseconds, what we will say that is our delta time is fixed to being 16 milliseconds. So if we get 100 milliseconds, then we will take several of those 16 millisecond steps until we sort of catch up. And that way things will behave nicely again, even though you got this kind of hitch in the frame rate. It won't just have things go through for other things. So the first thing we will do here is we will take this dt thing here, and I will change it to be a constant. So I will say dt is 1.0 over 60. This is 1 second divided by 60. This is roughly equal to 16 milliseconds, or in seconds counted 0.016 seconds. So this is the fixed time step we will use. Now this code down here, of course, won't compile anymore. What we instead want to do is to add this frame time. How long was the previous frame? We want to add that to some kind of counter that sort of accumulates this time. And then we want to step a number of times with the time with this new dt constant, and then slowly drain this accumulated time. So here instead I want to do like this: accumulated time plus equals rl.getFrameTime. So then we go up here and we add in accumulated time is an f32. Okay, so now we have a constant time and we accumulate time. So what will happen now is that all the stuff that used to happen down here needs to happen several times until accumulated time is smaller than this dt constant. So what we'll do here is we will make a loop that says for accumulated time is bigger or equals to dt. So this loop here will run as many times it needs until accumulated time is smaller than this delta time. So we sort of consume the accumulated time in chunks of this fixed size dt. So we need to put essentially all the update code of our game. All of this. We mark it, press tab to indent it, and then we put the new curly brace at the bottom here just before begin drawing. Now we see that we have this dt here. We need to replace this dt with that one, and then there are probably a few more. Okay, search for dt. This one here, and then maybe that was it. I think there's only 2 of them. Yeah. So now we're using the fixed time here, and we're using the fixed time here to move essentially the ball and the paddle. We also need to decrease accumulated time by dt for each lap of the loop. So we will go down to the bottom here and write accumulated time minus equals dt. So that's how it, for each lap of the loop, drains accumulated time by steps of dt. Also, I realized this previous ball pos here should of course be inside there. If we now build and run the game, we can launch the ball and grab the window handle. This makes the delta time become very big, and then we see that it was here, it did bounce in here, and then it went up like this, and then it has chewed away lots of blocks on top. We can also try changing the target frame rate to 10 again and play. Even though it's a bit hard to play, the ball won't go through anything in an unexpected way, because it is computing those in between fixed time step frames correctly. Change that back to 500. Now there's one last thing we need to do with this, because one thing that happens here is that, for example, accumulated time, say that it is like 0.031 seconds, then if this loop runs once, then it will be decreased by roughly 0.016, so it will be then like 0.015. Then this condition is no longer true, so we cannot run this loop once more, but you almost have a full frame worth of time here. So if you think of your ball moving, it should almost have moved to a new spot, but there wasn't enough time in the accumulator for it to do so. In that case, it would be nice if we could sort of smoothly move the ball for any value between when the accumulator is 0 and when it hits dt, so sort of even it out, that time in between for when it actually cannot run this loop. So that's the last thing we're gonna add in here. In order to do that, we must know where was the ball previously and where was the paddle previously. We will put those things as sort of global variables because we need them after this loop has finished, and we also, if this loop doesn't run at all, we still want the value from the previous frame. So we already have previous ball position here. Let's change that to an equal sign, and then we write previous paddle position equals paddle pos. Previous paddle pos x equals paddle pos x. Now we need to create these two variables. So we go to the top here. Previous ball pos is an rl.vector2, and previous paddle pos x is just an f32 because that's just the x component. That's the only one that changes for the paddle. So now we are doing these two things. We're setting them up each frame. So if this one doesn't run at all because maybe we didn't accumulate enough time, maybe we only accumulated less than dt, then it will still have the value of the previous frame in these whenever it most recently updated them. So what we can do then is just after the fixed time step loop happens, we can add in a little blending thing that blends the previous position with the current one using this remaining time. So first we'll calculate this blend factor that we use to blend the previous with the current state. So we say blend : equals accumulated time divided by dt. Then we need to know where should the ball be rendered right now, and we don't want to change, like the position the ball is on should not be changed. That should only be changed by the fixed time step loop up here, but we can calculate this a new position for where to render it that uses this blending. So we can write ball render pos colon equals math.lerp. Lerp is linear interpolation, so we can say that we want to go from the previous ball pos to ball pos, and this value blend will always be between 0 and 1, because after the fixed time step loop up here is done, accumulated time will always be larger or equals to 0, but not greater than dt. So this thing here will result in a value between 0 and 1. And lerp, when blend here is 0, it will pick this value. When it is 1, it will pick this value, and then it will sort of blend them in between. Similarly, we can do a paddle render pos x, and that is a math.lerp from previous paddle pos x to paddle pos x with the blend factor. And now we just need to take these two, and we go down here and we say where we render the ball, we instead say ball render pos, and here we say paddle render pos x. And now if we compile and run the game, everything is wrong. We actually see that there's two things that are wrong here. The ball is up here and the paddle is here. That's because time hasn't yet started, and these two are just zeroed out. So let's just quickly fix that. We will go to reset, and in here we will say previous ball pos is ball pos, and then previous paddle pos x is paddle pos x, and then I think also we'll need to change it here where we are updating manually the ball position. Ball previous ball pos is ball pos, like that. If we now compile and run this, you see that it works correctly, and we can play the game just like before. Now this last thing here is, like, if you look into this article that I showed previously, this person explains why you need to do this. And if you had a game with maybe more motion of the camera and stuff, the lack of this blending step at the end would become quite obvious at some weird frame rates where you always get like a lot left over in the accumulator, or you maybe quite often don't get a single frame. So like maybe you only get like a frame every other frame. So one frame you have enough time in the accumulator to update, the next frame you don't, the next frame you have, then it can get kind of this weird hitchy, or whatever you want to call it, feeling. And this sort of fixes that. Keep in mind though that this does not use, this uses the previous ball position to the current one. So in theory this adds a lag of up to, on average, like half a frame, because you will almost never see the ball pos at its most recent value. It will be a blend between the previous one and the current one. You could, in theory, extrapolate a future ball position using the direction and the velocity. That's much more complicated, and it's also not certainly correct, because it can maybe the input changes the next frame, so your prediction was actually wrong. But in some cases you could do that. Also note that, like, here we are explicitly calculating the ball render pos using some global variable here and some other variable here. If you have a big game, maybe you have thousands of things. What you can do instead is to have two copies of the game state. You have the previous game state, and then you have the current one. So that way, whenever you want to draw the game, you can just feed in, here's the previous one, and here's the current one, and here is this blend factor. So then whenever it fetches anything from in there, it can sort of use the previous frame plus the new one and the blend factor, and then you can probably build some little system around that to make sure that it always uses the previous and the current one. Okay, that's the last thing we were gonna do here today. In the description, you will find a list of ideas for improvements that you can do to this game. And I would love to hear if you've created this game and you improved it in any way of your own, then just hop on my Discord server and post a picture or video of it or something. That would be very fun to see. I want to thank my patrons, which are these people that support me by giving monthly donations on Patreon. And I also want to give a special thanks to my super supporter, Ian Seckington. If you like these videos and want to support me, then you can do so by becoming a patron. The link to that is in the description of this video. That's it. Have a nice day and happy programming. Bye bye.